right, Gen Chem, we are going to skip a few lines. So if you go to the next page in your workbook, we're going to start right here. Okay. It's going to say, after discovering 3 subatomic particles. Now, the 3 subatomic particles that they discovered, let's review because it's been a long time since we've talked about them. They discovered protons, and remember, protons are positively charged, and they are in the nucleus. They also discovered neutrons that are not charged at all. They are also in the nucleus, and they discovered electrons, and they are charged negatively, and they are outside the nucleus. So we have these in the nucleus and these electrons outside the nucleus. Of the atom. Okay, so we are going to really be talking about electrons. So electrons are what we're going to be talking about, and we're going to be talking about energy of electrons and wavelength and frequency. So all of these things we can measure on electrons depending on their behavior. Okay. So after discovering those 3 subatomic particles, proton, neutron, and electron, in the early 1900s, scientists continued their quest to understand the atomic structure and where things were in the atom and why they acted the way they did. So we are going to talk about the arrangements of electrons and atoms. We already talked about the energy levels, and we did the Bohr model, and now we're going to talk about why Niels Bohr came up with the idea that he did for his energy levels and the Bohr model. But to do that, we're going to have to talk about light for just a day or two so that you understand where this idea came from. To understand the further advances in atomic theory, we're going to have a light discussion about light. Okay? There are 2 variables that relate to a beam of light. Okay? These variables are wavelength, and we designate wavelength by lambda. Okay? And we also have frequency, and we designate frequency by nu. So these are some Greek letters, lambda and nu. Okay? So let's look at how we measure wavelength. And I think I talked a little bit about this. Wavelength is measured from the same point of a wave. So if I'm measuring from the top, I'm going to go to the top of the next cycle. Or I could measure from the bottom, or called the trough, to the trough of the next cycle. It doesn't really matter where I measure from, just as long as it's the same point in each cycle. And that will give me a wavelength. And wavelength is given to us in meters. And meters, of course, is a distance. Okay, so we would expect our measurement to be a distance, which is meters. Now, frequency is measured in number of cycles per second. So it's how many wave cycles go through a given point in 1 second. Okay, so if I look at this, and sometimes frequency is also, we will do number of cycles per second. This is also called hertz. Okay, hertz just means cycles per second. So if I do wavelength, which is in meters, and I do frequency and I multiply them together, so I will have meters times 1/second. I get the unit of meters per second. And meters per second is a speed or a velocity. It tells me how fast something is going. And guess what? This stuff is all traveling at the speed of light. It's part of the electromagnetic spectrum, right? So the value of the velocity of light is 3.00 times 8 times 10 to the 8th meters per second. So that's like 300,000 kilometers per second. It's very, very fast. Okay? So if I know wavelength, I can isolate it to frequency. So for example, if I know wavelength and I want to know frequency, my frequency is going to be the speed of light divided by wavelength. Or if I know frequency and I want to know wavelength, wavelength is going to be the speed of light divided by frequency. So if I know one, because the speed of light is constant, it is a constant, I can find the other. Okay, so we are going to use this relationship for a lot of these equations. And you are going to definitely want a calculator here. Okay, now you'll notice that we're using exponents times 10 to the 8th or times 10 to the whatever. If you have questions how to enter this onto your calculator, please come and see me. Each calculator is different. If you have a TI though, if you have a Texas Instrument calculator, there is a function on your second function. So if you use your second function button, there should be a key, and it's usually the key right above the 7 that has this EE symbol on it. That EE symbol is 10 times something to the x, where you can put in the x. So that gives you the scientific notation of 10 to the whatever. So it's right above the 7 key. On most TIs, you should see a EE, and it's a second function. And you're going to want to use that to put in your powers of 10 for these numbers. It makes things a lot easier. Okay, so here we go. Let's look at frequency really quickly. So I'm going to pretend that this is 1 second. So through this time, this is 1 second. And I want to know what the frequency of both of these waves are. Okay, so if you remember, frequency is number of cycles per second. Okay, so all I have to do is count the cycles. So I'm going to count here. I'm going to start here. So I've got 1, 2, 3, 4 cycles in that 1 second. So the red line has a frequency of 4 cycles per second, or we'd say 4 hertz. Okay, let's look at this purple line. Let's count how many cycles we have here. We have 1, 2, 3, 4, 5, 6, 7. We have 7 cycles. So the purple or the violet line, I can't spell, purple wavelength has 7 cycles per second. So we could also say that as 7 hertz. Okay, so we already went over this. The speed of light is equal to the wavelength times the frequency. Remember, C is a constant. It's 3.00 times 10 to the 8th meters per second. Okay, this is a constant. It does not change for anything on the whole electromagnetic spectrum. They all are traveling at the speed of light. So if I want to isolate wavelength here, wavelength would be the speed of light divided by the frequency. And if I want to isolate frequency, it will be speed of light divided by wavelength. So we're going to use those relationships over and over and over again. Okay, so let's learn how to do some of these calculations. What is the frequency of a beam of red light which has a wavelength of 675 nanometers? Now the thing that we have to do is the speed of light is in meters. So we need to get this into meters. So how many nanometers are there in a meter? Do you know your metric system very well? If you don't, it's okay to look it up. So I have 10 to the ninth, or 1 billion nanometers in a meter. So I'm going to use that equivalence to convert from nanometers to meters. Okay? I want to know the frequency. So I'm going to start with the speed of light is equal to wavelength times frequency, and I'm going to isolate frequency. So frequency is going to be the speed of light divided by wavelength. Okay, remember, speed of light is a constant. So I have 3.00 times 10 to the 8th meters per second. Okay, now I need to divide by my wavelength. My wavelength's given to me right here. I have 675 nanometers. But notice that this is meters and this is in nanometers. And I can't cancel out, so I need to convert the nanometers to meters. So I'm going to use this equivalence here. I have 10 to the ninth nanometers in 1 meter. And that way my meters can cancel out and my nanometers cancel out. And I'm left with per second, or hertz, which is what I want for my frequency. So we are going to put this into our calculator here. And I want you to put it in step by step. So we're going to put in 3 times 10 to the 8th. So when you put in 3 times 10 to the 8th, you're going to type 3, and then you're going to find that second function button and hit that EE button and type in 8. And you should get this for, well, I'm turning that the wrong way. You should get this for your calculator screen. That is how it should look when you put that in. Okay? Then we're going to divide by 675. And then our next step, we need to multiply it because the 10 to the ninth is on the top. We're going to multiply by 10. And then this one, you're going to want to use your caret key. And the caret key is right above the divide sign. So this little caret key, 10 to the ninth. And we will get, let's see, we've got 3 digits here and we've got 3 digits here. So we're going to report 3 digits. We will get 4.44 times 10 to the 14th per seconds, because we're left with the unit per second. Everything else is canceled out. Or we could write this as 4.44 times 10 to the 14th hertz, because hertz is just per second. Okay, what's a wavelength? So now we're going to look at wavelength here. So I'm going to start with the speed of light once again. So speed of light is equal to wavelength times frequency. And I want to isolate for wavelength. So wavelength is speed of light divided by frequency. Okay? So our speed of light is a constant. It's 3.00 times 10 to the 8th meters per second. That M is not very good. And I want to divide by my frequency. Now this second times 10 to the negative 1 really means per second, or divided by second. So if I put this on the bottom, 2.7 times 10 to the 14th, and the second was on the bottom, it now becomes part of the top. So that means seconds cancel, and I'm left with meters. And that's what we should get for wavelength. We want a distance. Okay? So we're going to type in 3 times 10 to the 8th, and in order to type in 3 times 10 to the 8th, we're going to type in 3.00 second EE8. So once again, this is how you should have that on your calculator. 3.00 E8, or 10 to the 8th. Okay? And then we're going to divide by 2.7 second E14. So that's how you should have that second in there. So that works. Okay. So we've got, let's see, we've got 3 digits here. We've got 2 digits here. So we're probably going to just report 2 digits. So I have 1.1 times 10 to the negative 6 meters for that wavelength. Okay? Now, objects get their color from reflecting only certain wavelengths. So for example, my sweater that I'm wearing today is blue. So it's actually absorbing all the wavelengths in the visible light spectrum except for blue. And it's reflecting the blue to you so that you can see the blue. And that's what's going on in your eyes. The light reflected from a green leaf is found to have a wavelength of 4.9 times 10 to the negative 7 meters. What is the frequency of the light? So, once again, we're going to use this equation where frequency is equal to the speed of light divided by wavelength. So we have our speed of light as 3.00 times 10 to the 8th meters per second. And we're going to divide by our wavelength. And this time it's in meters, so we don't have to convert it. We can leave it in meters. So 4.90 times 10 to the negative 7 meters. And that means our meters cancel out. So we're left with per second, which is exactly what we want for our frequency. So we're going to take 3 times 10 to the 8th, and we're going to divide it by 4.9 times 10 to the negative 7th. Remember to use that EE button. And we've got 3 sig figs on both, or 3 digits on both of these, so we're going to do 3 digits. We'll get 6.12 times 10 to the 14th. Now this could be per second, or we could do 6.12 times 10 to the 14th hertz. Either way, it means the same thing. Okay, so either way, that would be a good report. Okay, so let's do another practice problem. After careful analysis, an electromagnetic wave is found to have a frequency of 7.8 times 10 to the 6 hertz. What is the speed of the wave? Okay, so remember, the speed is equal to frequency times the wavelength. And remember, the speed of all of these is the speed of light. All of this electromagnetic wavelength all travels at the speed of light. So that's 3 times 10 to the 8th meters per second. It is a constant. It does not change. So beware of these trick questions that ask you anything about a constant. It doesn't change. The speed stays the same. Okay, so this next bit, we're going to start talking about the energy that these different waves and frequencies have. Okay? In his attempt to explain the hydrogen spectrum, so there's a spectrum of light that we see that we'll talk about next time when we look at hydrogen through a prism. We get 4 lines. We get a blue line, a purple line, a green line, and a red line. And we can see different lines on different elements, and we'll talk about identifying different elements by their spectrum next time. So this is Niels Bohr. This is the guy who came up with the Bohr model of the atom that we use to figure out different energy levels. Okay? In his attempt to explain the hydrogen atom, Bohr developed his planetary model of the atom. Okay? So the planetary model is one where we have the nucleus in the center, and then we have electron orbits that go around that nucleus. Okay, so the electrons are in orbit around the nucleus. Kind of like the planets in our solar system are in orbit around the sun. So think of the sun as the nucleus and the various planets on different energy levels in orbit. So for example, the closest planet to the sun, Mercury, would be in the lowest energy orbit. And then we would have Venus, a little bit more energy. And then here, Earth, a little bit more energy, and then a little bit more energy farther away from that nucleus would be Mars, and so on and so forth. Okay, so the farther the orbit is, the more energy that electron has. The closer that orbit is to the nucleus, the less energy that electron has. So this is the model that Niels Bohr created. Okay. Bohr used quantum theory, a theory of energy emission that had been stated by a German physicist, Max Planck. Planck assumed that energy, instead of being given off continuously, was given off in little packets or quanta, energy chunks, for lack of a better word. Quanta of energy are called photons, and we use photons all the time. That's how we see. Photons come into our eyes and allow us to see. He further stated that the amount of energy given off is directly related to the frequency. So energy is proportional to frequency. So if I drew that out and I had energy and frequency, I would have a line like that. It's proportional. When frequency gets bigger, energy gets bigger. Replacing that alpha sign with an equal sign means that we have to use a constant, a proportionality constant. So we use this equation where energy is equal to Planck's constant times the frequency. And Planck's constant is this, 6.6262 times 10 to the negative 34 joules times second per photon. So I want to do an example problem with you. So let me look one up really quick, and we will do an example problem, probably two of them actually, because I want you to be able to do one with frequency and one with wavelength, because you're going to be doing both of those. Okay? So notice in this graph that I did over here that as frequency increases, let's do a couple of these graphs. So if I have frequency increasing, wavelength, because we have speed of light times wavelength, we have an inverse relationship. Okay, so as frequency increases, wavelength actually decreases. They are inversely proportional. But as frequency increases, energy over here increases because they are proportional. Okay, so we have a couple of relationships here that we are going to be using. Okay, first example, I have, let's see, I have energy. I want to know what the energy of a frequency of red light is. The red light has a frequency of 4.48 times 10 to the 14th hertz. And I want to know what that energy is. So I'm going to use this equation where I have energy is equal to Planck's constant times the frequency. So I'm going to have energy is equal to 6.6262 times 10 to the negative 34 joules times second all over photon. And then I'm going to multiply it by the frequency, which is 4.48 times 10 to the 14th. And hertz is really per second. So the seconds cancel out, and I'm left with joules per photon. Joules is just a matter of energy. Okay? So once again, we're going to use our EE key to do these powers of 10. So I'm going to type in 6.6262 second E negative 34 times 4.48 second EE 14 to get that power of 10. And that will give me an energy of 2.97 times 10 to the negative 19 joules. Okay? Now, if I had red light, we're going to just still focus on red light. What if my red light had a wavelength of about 450 nanometers? what would be the energy there? Where's the energy there? So we're going to use this relationship. Can I substitute this relationship in? So if I do frequency, it is the speed of light divided by wavelength. So if I substitute this for frequency, that means energy is going to be Planck's constant times the speed of light divided by wavelength. So I'm going to use this to find my energy. So energy is equal to Planck's constant times the speed of light divided by wavelength. So I'm going to type in 6.6262 times 10 to the negative 34 joules second photon. And then I'm going to multiply it by the speed of light, which is 3 times 10 to the 8th meters per second. So my seconds cancel. And then I'm going to divide by my wavelength, which, oops, I'm so running out of room. Let's see. Divide by my wavelength, which is 450 nanometers, but this is in meters, so I need to convert that. So I'm also going to have to multiply it by 10 to the 9th nanometers to get into meters. Okay, so we're going to take 3 times 10 to the 8th, and we're going to multiply it by Planck's constant, which is 6.6262 times 10 to the negative 34. And we're going to divide it by our wavelength, which is 450 nanometers. We're going to multiply it by 1 billion because there are 1 billion nanometers in a meter. And we get an energy of 4.42 times 10 to the negative 19 joules per photon. Okay, so we can figure out the energy that we have in a wave if we know the frequency or the wavelength. So if we use the frequency, we're going to use this